Oui, donc, bonsoir à tous. Merci d'être venus en grand nombre ce soir et merci à l'Université de Sherbrooke, campus de Longueuil, pour être l'hôte de cet événement et de nous avoir aidé à organiser l'événement. Je m'appelle Mathieu, je suis vice-président de l'Association du vol vertical, section Montréal-Ottawa, which is also known as the Vertical Flight Society, Montréal-Ottawa Chapter. As some of you may recognize, we slightly changed the logo of the Vertical Flight Society Montréal-Ottawa Chapter. You will see a bit, it's a little change, but later on this year and maybe for our next event, we'll have maybe some other surprise to show related with some little change that we are working on presently to be able to give you more benefit when you participate to our event. So the title of our event tonight, The Science and Future of Helicopter Flight. So who we are, the Vertical Flight Society Chapter Montréal-Ottawa. We are a multiple person working in different fields of the aerospace industry. A lot of us are working from Bell Helicopter, other CAE, and other companies related in the Montreal-Ottawa region. And we also have the McGill VFS chapter. I think you are there tonight. Thank you for your participation. And if there's other students for other university who would like to start a local VFS chapter or would like maybe to merge their current technical project with the Vertical Flight Society to get a bit more benefit, you can reach out to any of us tonight to learn a bit more, and it will be a pleasure to discuss with you. So what we do and what is our mission at the Vertical Flight Society is to increase the interest in vertical flight across Canada, create platforms to facilitate networking and collaboration, and to provide learning opportunity through exclusive conference. So what we do tonight with this event, the goal is to accomplish those three missions. And if some of you would like to be more involved into the Vertical Flight Society and join our chapter as an officer, for example, it would be a pleasure for us. Please reach out to us. And if you maybe you have an idea for an event or a person of contact, you can reach to us, and the VFS can be the bridge between your idea and an event as the one we are doing tonight. A few things that we do at the Vertical Flight Society. We are involved with the student in February 2024. We provide some judging capacity and our experience for a student case competition at the McGill University. We have some event at Pratt & Whitney, for example, in last May, and some event in the Ottawa region in April last year. We also sometimes we have event in university or in company, and sometimes we like to have some event at a restaurant, as for example in 2024 at the Trois Brassards. We are so involved into the Montreal aerospace industry and participate to some conference as we did in May 2024. And we are very happy this year. We received the award of the largest VFS membership increase in 1 year. So you are one of the main contributor to that by joining the VFS community and participate to our events. So good thanks for that. We have a few celebrations to mark tonight. So two companies reach several milestones this year. If we start with Pratt & Whitney, they celebrate then their 100 years of powering the future. If we can bring a couple of numbers, it's more than 90,000 engines in service, more than 45,000 employees. And if you think about that, like every second, a Pratt & Whitney powered aircraft take off or land somewhere in the world. And at the same time, so this year, Bell is celebrating its 90 years. So if we go with the main topic of tonight's presentation, we'll have two presentations. The first one is the fundamental of helicopter aerodynamics that will be presented by Mathieu Bouchard, who is a research engineer with the Createk Innovation Group at the Université de Sherbrooke. And after that, we'll have a brief period of question. And the second presentation will be an alternative propulsion system that will be presented by Professor David Rancourt, who is an associate professor at the University of Sherbrooke, a commercial pilot, and involved with the AéroUdeS Institute Director and Createk. So our first presentation on fundamental and helicopter aerodynamics will be presented by Mathieu Bouchard. Mathieu is a research engineer with the Createk Innovation Group at the University of Sherbrooke. Over the past 5 years, he has led numerous research projects on alternative propulsion in collaboration with industry partners, as well as projects focusing on the design of propeller for unconventional aircraft. He also taught the course of aerodynamic and helicopter performance for 5 years. He holds a master's degree in mechanical engineering with a focus on optimizing the performance of an autonomous tandem helicopter, and he is currently pursuing a doctorate in the design of propeller for atypical flight regime.
All right. I hope you guys are ready for 500 slides of material. Just kidding. So this is a bit of a kind of really distilled down version of the course we teach at Sherbrooke. So it's actually the 5th year I'm teaching it. Before that, David brought up the course, which I actually followed when I was at my bachelor's degree back in 2019, 2020, something like that. So actually, I never realized how much I worked on rotorcraft and propellers that much. One of the things that's not mentioned in the bio, which I did not add, but my capstone engineering project during my bachelor's was actually to make a overbike. So again, playing with propellers, although it did not fly at the end, but still a fun project. So we're gonna try to kind of really go over just the really most basic fundamentals of helicopter flight. It's one of kind of the, I'd say one of the weirdest and one of the most complex kind of flying vehicles out there. So it's kind of hard to just give a 30-minute presentation on the overall workarounds of the aircraft. So to begin, actually, typically end my classes with kind of either a historical quote or a funny quote I found online on helicopters. So I thought this one was a pretty good one. So I think it's a pretty good representation of what helicopters are, although that might change a bit in the future. But it is kind of a lot of vibrations and pieces flying around the air, waiting for something to happen. So it's a good summary of what an helicopter is. So first things first, actually not talking about helicopters, but rather fixed wing aircraft. So I'm thinking an assumption here that you're all pretty much familiar with aerodynamic efficiency metrics, so L/D. If not, the higher, the better. So you just want to have the highest number possible. There's a nice little figure there that I took from some classic manuals, so Raymer for those who know. The x-axis doesn't matter here. Basically, the only thing you need to know is that the higher, the better here, and there's a bunch of aircraft which exist. One we all know about is, for example, the 747, which has a L/D of about 18. So that's a pretty good aircraft. There are better, more aerodynamic aircraft out there, but it's still pretty good efficiency there. On the lower end of it, if you ignore the military aircraft there, you have what the kind of aircraft David might fly, so a small general aviation aircraft, more of a brick with wings, but still an L/D of about 10, and that's typical of these kinds of aircraft out there. So fixed wing aircraft are somewhat efficient. Rotorcraft are not at all. So similar figure, L/D on the left, the higher the better, although this one ends at 10 with the Piper Cherokee out there with its L/D max. And then you have the speed on the x-axis, which is not too important here. If you compare your typical helicopters, so here you have a UH-60 Blackhawk and a tandem, so the Chinook tandem helicopter. You at most, if we're being generous, have maybe 4.55 of LROD. So that's half the efficiency of a brick with wings that you can kind of fly for pleasure and not for long distances. So kind of limited, and although those are not the most recent models, it's pretty representative of typical efficiency for rotorcraft. There is other models kind of cheating a bit with compound helicopters, which add wings and add propellers to it. You can kind of get better efficiency, but not that much. Same thing with tilt rotors that are kind of not helicopters at that point. But even in kind of airplane mode, they're still pretty limited in terms of aerodynamic efficiency. So if you want to fly around, go fast or go long distances, you're not kind of your best bet is not to take an helicopter, rather just take a plane. But they do serve a really important purpose, and which is that fixed wing aircraft are actually limited in terms of speeds they can go when we're talking about really going slow. So sadly, with an aircraft, they tend to fall out of the sky if you go too slow, which is not the case with any kind of rotorcraft, which is the only advantage they have. So main advantages, the only reason you might want to fly a helicopter, well, if you can't have access to a runway and want to land vertically, they're the only option. Do any kind of strong load operation, so lift cargo from the air vertically, that with an aircraft, a fixed wing aircraft. Or this little quote from Igor Sikorsky, which for some reason the Sikorsky disappeared. So if you want to take rescue a man who's in need of help, an airplane can come in and throw flowers at him, but you can bring him up. So an helicopter might be able to do actual search and rescue. With an airplane, you might spot the person, but you're going to leave him there. So pretty useful as that purpose. One other aspect, though, is for some reason now it's a pretty good solution if you want to explore outside the Earth. So any kind of planetary exploration, although typically fixed-wing aircraft are good for long distances, you're not going to beat rotorcraft if you want to explore Mars or if you want to explore Titan. So really long distances, helicopters are kind of better than fixed-wing aircraft at that point, although those are pretty fancy aircraft. And you can kind of cheat a little. So if you want to go faster, you want to go higher, maybe longer distances. I mean, obviously, your typical aircraft in here, it's a turboprop. It's not the most efficient, but it's a pretty nice aircraft. Can do way faster and way higher, and thus longer range than your typical helicopter. Here, the Bell 505. Just one mention, the flight envelopes there, the numbers don't match the aircraft necessarily. They're just nice pictures. So if you cheat a bit, add wings, add propellers to your helicopter, you might get higher speeds. In this case, the Airbus Racer, which you see on the screen, was actually did a demonstration a few months ago, and I think they reached about 440 kilometers an hour. So that's a world record in terms of speed you can achieve with helicopters. It's not exactly something you'd fly every day. It's still just a demonstrator. And at that point, you're more of an airplane as you get along with adding bigger wings and more propulsors. Another way to cheat, again, is to add wings, but also to kind of tilt your rotors. So in this case, for a tilt rotor aircraft, you would actually call them prop rotors. But you can go way higher and even then kind of bridge the gap and go faster speeds, kind of like a mix match between an helicopter and a turboprop aircraft. Although right now there is no civilian version that's certified, so it's kind of limited in their use case for military applications. So that's kind of the overall topo on if you should choose an airplane or if you choose an helicopter or any of the kind of bastardized versions of the helicopter. If you want to go long distances, I'd recommend using a fixed-wing aircraft unless you don't have any runway access. And that's not something that's going to change a lot over the next decades. So there's gains that can be made, but it's always going to be less efficient than the airplane. Now, I'm going to show you a few, not really formulas, but kind of proportionality ratios, which are interesting. So one aspect when it comes to vertical flight, The bigger, the better. There's no way around it. So the bigger the rotor, you're going to be more efficient. So whether you're comparing yourself to a F-35 fighter jet that can do VTOL or a eVTOL like Lilium, whose figure actually is here on the display, if you have a bigger rotor, a bigger propeller, you're going to be more efficient and going to be able to lift more weight for the same amount of power, so for the same engine. So there is no way to beat that. So the helicopter is always going to be the more efficient in terms of vertical flight. One other aspect, so if you're going to land anywhere in an urban environment, or let's say a small park with children playing around, you don't want to have a large downwash velocity that could kind of throw rocks around or just throw people down on their back. So the bigger the rotor, again, it's going to be a lower downwash velocity, so something much safer. Much less of a risk. So when it comes to the choice there, the bigger the rotor, the better you're going to get. Also, here, just in terms of safety, one of the things that do happen is you can lose power. So if your engine shut down in the middle of the flight, an helicopter, although it can glide, can still actually kind of somewhat glide and land safely, actually quite well. But you need rotational inertia, so the bigger the rotor, the easier it's going to get to have a safe landing if you lose your engine. Not the case if you have really small rotors or propellers, where that might not be the case, and you're going to need some other way to ensure you can safely land if you lose engine power. Obviously, there's still some limitations to that, so the bigger the better doesn't always work. If you have something which is as big as this room, at some point you're not going to be able to land anywhere. So there are limits in terms of weight, just other design criteria. So until you hit that constraint, though, you want to have the bigger rotor if possible. There's no reason really to go for a smaller rotor diameter. The thing is, helicopters, well, they're good for vertical flight. They're extremely efficient, but you still want to go somewhere with your helicopter. So unless you just want some kind of elevator, you're going to need to go forward. And that's where you lose all your efficiency and things get really complicated. So for this presentation, I'm going to keep it to the most basic problem with helicopters, which is the fact that you have one blade that's advancing towards the direction of flight and one which is coming back in the opposite direction, and both see completely different velocities, and thus creates a bit of a problem when it comes to generating a lift. So that main problem is what's called the symmetry of lift. So one side of the rotor, which in this case here turns counterclockwise, so with the magenta arrow. So the blade going forward in the direction of travel sees much higher velocities than the blade coming back. But that means that the blade going forward generates more lift than the blade going back. So that's a bit of an issue. So what you get is that instead of having a nice airplane wing, which travels at a constant speed and sees the same kind of airflow velocity over the entire wing, you have basically a rotating wing, which every second will see a different flight condition, and that's for the entire flight. So you have to try to design basically a wing which will operate in two completely different regimes, one which is near high speeds, transonic flight, and the other which can end up being near stall, which is where airplanes typically have an issue. So it's also going to be an issue for an helicopter rotor. So that's the most basic issue with helicopter flight in the joyous flight. So fundamental issue, the symmetry of flight. What that does is basically creates a rolling moment, which historically, so about 100 years ago, ended up with the initial prototypes, so actually gyrocopters, just rolling over on their side when trying to go forward. So that's not really something which is useful for an helicopter. So that's where basically all the complexity of the rotor comes from, with trying to rein in that problem and balance that rolling moment. So that's something we want. Also an issue in terms of structural loads. So the solution is quite simple. If the blade wants to go up, well, you might as well just let it go up and then let it go down again. So don't try to fight it, just let it do its thing. So you basically have what we call blade flapping, with the just kind of going up and down in a sinusoidal motion pretty much during the entire flight. What that does is, if we cheat a little, I think no need to go too much over that. There's going to be some equilibrium which is going to be reached at some point, and basically you will balance that moment, and the aircraft will not try to roll over on its side anymore. So you end up with the little flapping hinges there, which is why rotors will typically have a flapping hinge, which we don't have on this type of propeller, type of rotor, but which will allow it to go up and down by itself. There is a little issue though that comes out of this. So you end up with basically a displacement of the center of gravity of the blades. And globally what that means is that if you don't take care of that problem, you're going to end up with a blade which will have extremely high loads in terms of the in-plane motion, and it would simply break off, which is also what happened about 100 years ago when De La Servia was trying to fly his gyroplane. Well, just again, the same solution functions. So just let it move forward and backwards by itself. There's no need to try and stop it. So that's where the lead lag hinge, so an additional hinge where we let the blade now flap up and down, but also forward and backwards comes from. Little issue though, so on some types of helicopters, some type of rotors, you're going to end up with possible ground resonance. And if any of you have seen those kind of videos, basically the entire helicopter will self-destruct if the pilot doesn't come off the ground. And that's something that's inherent with the type of design. If you let your blades go forward and backwards and then don't do something about it, it can happen, and it's just the nature of it. One of the solutions is to add dampers to it to try and damp the motion, but there's still always a possibility of that happening, just it's more controlled than before. Sadly, if you want to have a rotor which goes forward, you're going to end up with something complicated like that, which will have to allow the blades to go up, down, forward, and backwards. And there's no really any other way of going around that problem. So that's the most basic aerodynamic issue. And then what that means is you get an extremely complicated rotor system. And with Aero, actually, it's not the most complicated looking version. So there's pictures which look even worse than this. But you have mechanical hinges which will actually allow the blade to go up and down and backwards and forwards for every blade. You also have a hinge which will allow the blade to actually rotate so you can change the pitch angle. Otherwise, you're kind of stuck not being able to control the kind of thrust you're generating. So that's 3 basically hinges for every blade, plus a bunch of other mechanisms. So that's an extremely complex piece of machinery. So that means high maintenance cost, high parasite drag if you want to go fast. So it's a bit an issue. On this REC aircraft rotor, it's kind of really simple, but that's not your typical looking. So the end goal is typically to kind of try and reduce that mechanical complexity, try to get maintenance costs down as much as possible. The issue is that you're typically going to end up with really complicated designs in terms of the design process itself. In between those, you have what you're maybe used to seeing on Robinson helicopters, which is the tethering rotor. So those simplified work only for 2-bladed rotors. They're already relatively simple, but they have some really inherent flaws, such as you can't actually do any kind of low-G flight. So if you're in a helicopter and try to kind of rapidly go down the side of the hill, you will potentially basically lose control, and you might, depending on the rotor design, end up with mass bumping, which could lead to rotor separation or a tail boom strike. So they can be dangerous depending on the type of rotor. So you're not going to do any aerobatics Red Bull style with that kind of rotor inside. You're going to be limited to kind of nice little flight over the city to kind of view the sights. A bit more complicated in terms of design, but much less complicated mechanically. You actually have here a bell rotor head, which is hingeless. So the idea is get rid of the mechanical systems. So instead of having actual mechanical hinges to allow the blades to move forward and backwards, you just let the blades bend by themselves. So there is actual flexibility in the blade design to allow that motion to exist. So the blade still goes up and down, still goes backwards and forwards, but it's actually bending either the blade or a piece of it which is made to bend rather than having mechanical hinges. So we end up with a more simple mechanical design, so less maintenance cost and hopefully more aerodynamic in terms of drag later on. The more extreme version of this is you also remove the bearings and basically to try and change the pitch angle of the blade to actually bend the flex to rotor tube. So you're actually bending part of the blade system rather than having an actual hinge with a bearing to allow the blade to change angles. So that's even more of a bit of an extreme one. There's not many helicopters with those kind of rotors, but again, you have a more mechanically simple and aerodynamic blade system rather than the articulated rotor, which is your typical solution you'll find on most helicopters. So there's kind of another issue which comes up with the fact that we're letting the blades flap up and down. And it's that although you solve the kind of rollover moment problem, you also end up with another problem, which is that the rotor, the faster you go forward, tends to want to blow back behind. So it's still back. It tilts backwards. The faster you go, it's even more backwards. So unless you have some kind of propeller to pull you through the air, which is what you get with a gyrocopter, with an helicopter, there'd be no way to actually go forward because the thrust vector would actually bring you backwards. So to do that, you actually need to find a way to control when the flapping happens, so that you can kind of orient if you want, the plane of the rotor. So one aspect to understand is that if you're not aware, a rotor will not actually tilt fully forward, so the shaft will always be fixed with the airframe. But what you'll see when you see a rotor which seems to be tilted forward or sidewards is really just the tip of the blade which are bending in a direction, which kind of gives the idea that you have an actual tilt of the propeller of the rotor, but rather the hub is still fixed and the blade which is bending up or down. So to do that, that's when we typically, for most helicopters at least, have the swash plate system, which is what we have here, at least the part of it for this helicopter. So typically there would be another plate underneath, which basically allows you to either change the angles of all the blades at the same time, so you generate more thrust, can go faster or just go higher and lift more weight, or you can kind of tilt it on the side, which when you can turn the blades will basically have a different angle depending on which position you are. So one will be at a certain angle of attack while the other will be completely flat, and that will basically change when the lift is created, which will allow you to kind of play with the tilt of the propeller. So for most helicopters, that's what's used. Some designs like the Kaman's K-Max uses another system, but it's always the same principle. You're trying to kind of control using a sinusoidal approach, the blade pitch of the entire system to tilt it. So the faster you go, not only is the pilot just pushing the stick forward to go forward, but he's also basically trying to balance back the rotor tilting backwards. So he's always needs to put more cyclic forward to kind of bring back the rotor forward and then tilt it even more to go faster. And yeah, so it's much more complicated than that. So that's the just really, really basics. It's the fundamental problem which was solved about 100 years ago now, initially on gyrocopters and not on helicopters, funnily enough, but it's what basically allowed helicopters today to exist, and it's basically the fundamental principles behind every kind of helicopter now. In reality, you have much more problems than that. So as you go faster and faster, you'll reach kind of conditions where you have high speeds at the tip of the blades. So over here, you have transonic flow. So you can imagine you're getting some really high speeds there. While on the other side of the rotor, the same blade will basically start stalling and will get into higher kind of unsteady behavior, which is called dynamic stall, which today is still a subject of research, and there is no nice way to model it easily nowadays still. And that what's going to get you is, instead of having nice sinusoidal waves of thrust and just something similar, you'll get kind of really interesting patterns of loads which are generated and which the system must deal with. That's part of the reason you have so much noise and vibrations on the helicopter. It's basically a complex environment of aerodynamic interference coupling with the structure. There is interaction between the rotor and the fuselage under it, interaction between the main rotor and the tail rotor. So you have two rotors which operate in completely different conditions, and now they interact with each other. So you get some really interesting characteristics, including pretty interesting noise also. So all things which just makes the design and modeling of helicopters way more complex than a simple fixed wing aircraft where you assume you're going 100 kilometers per hour forward, and that's about it. So in this case, it's pretty complex. Obviously, we don't go that far into the modeling of those things during the course. We kind of stop at the main effects, but at the end of the course, students are actually able to model the performance of actually a Bell 505 and have a pretty good match with the actual specs from the manufacturer. So if you know what you're doing, you can get some pretty good results, even if you only have access to a few drawings and a few numbers from the marketing department. So kind of the review on Rotorcraft. And I kind of have a couple slides, kind of change the subject a bit and kind of discuss about propellers. So some of you might have seen that a lot of current aircraft designs, mainly VTOLs, kind of are starting to use propellers rather than rotors to kind of do the same kind of operations you'd see on the helicopter. So in a way, a propeller is really just kind of the limit case of a rigid propeller rotor. It's not exactly that, but it's pretty similar. Worst case, there is no blade flapping, there is no lead lag, there is no cyclic pitch control. Some don't even have collective control, so you can change the blade of the pull of the blade at all. So it's basically just RPM control. So that's a bit of an issue because they're not made to operate in those kinds of conditions. So I'm going to skip a little bit ahead, but one of the things I want you to get there is that those kind of flight characteristics are something which are a bit more typically understood by turboprop manufacturers. So although you don't get a turboprop flying the same kind of conditions as an helicopter, they do get some interesting alternating loads also, which you have to take into account in terms of bearing life and gearbox design, which is not the case for the kind of electric aircraft designs you see outside. And that's a bit of an issue for whether airplanes or eVTOLs, which are equipped with small motors, which have small bearings. And to give you an example of this, basically, Pipistrel had to reduce their time between overhaul for the aircraft in the past from nearly an order of magnitude because they had issues with the bearings. It's also what killed the NASA X-57 Maxwell prototype. So bearing life is a bit of an issue when it comes to electric motors, and that's something that it's not taken into account by most aircraft manufacturers of electric aircraft. So I'm skip the next slide and just kind of do a bit of an overview of self-promotion there, but there's something which is kind of missing a bit in the ecosystem here in Quebec, and honestly with a lot of manufacturers of propellers around the world. So having in the past done a lot of research contracts where we did actual design of propellers operating in kind of atypical conditions, there is kind of a lot of things that are not understood, and it's a lot of unknowns, and that's something we've been able to kind of help those manufacturers with by providing actual analysis capabilities for this. So we have our own models, which we've used and validated in the past, and something we're kind of pushing to develop more to kind of get to the level of what's used typically in the rotorcraft industry, just more modern than the old legacy code, which was written in Fortran kind of 30 years ago. And that includes also kind of doing our own experimental wind tunnel testing. So Sherbrooke actually has the largest wind tunnel in Quebec. It's honestly not in the best shape, but it's the biggest. So if you have any kind of fun things you want to test both experimentally, but also to kind of do actual propeller design or analysis, especially in kind of atypical conditions, we have the capabilities to do so, and we're continuing to develop those capabilities and validate them as we go along, as well as subscale propeller prototyping, which is pretty helpful for wind tunnel testing. Yeah, so that's about it. Pretty quick, but gives an idea. If you're interested, kind of the 3 books I'd recommend. Well, the first one is where I took all my figures nearly, mostly because it's a small update from the middle book, which is the textbook we use in the course at Sherbrooke. So the book by Leishman, the green one, is a pretty good overview of helicopter fundamentals and a good review of the more advanced topics without going too much into detail. If you kind of really want to go deep into the math and kind of overload yourself with a lot of equations, Wayne Johnson's Rotorcraft Aeromechanics is kind of the working Bible for this kind of stuff. Is one of the guys who wrote the kind of the comprehensive code that's used a lot in the industry. So you're gonna get a lot of math, but you're gonna get a lot of good details there. Just don't try to read it in one sitting. You're just gonna blow up. But the book in the middle is a pretty good overview of all of this, but the figures are better in the kind of first one, which is free and just an ebook online, listed by Embry-Riddle University. So it's a pretty good resource for quick browsing there. That's it.
Do you have any question? Est-ce que vous avez des questions à poser?
When Igor Sikorsky kind of was developing the helicopter, how did he know, or did they have the information about the gyrocopters, or how did he have that information?
Yeah, so you can still find, I think, some of the publications about that work initially that was done. So it was pretty well known. I think you can actually find the original drawings for the flapping and lead-lag hinges from the La Servia in the first book. So he has pictures, so there were patents, I think, and other documents. So it was well known at the time. It's just that it's kind of not something the helicopter industry themselves initially developed. So they were always trying to fly helicopters, but none of them really work. Either they just kind of hover a bit over the ground, but it's really kind of gyrocopters that kind of unlock that aspect. But at the time of Sikorsky, he knew about those, but nobody knew about the tail rotor though. So that was something else they discovered after.
What are some of the conditions that, what are some of the considerations that go into selecting the number of rotors in a design? 1, 3, 4, 5. Is what goes into that determination?
Well, for your more typical helicopters, you're not going to really go above 2. So there's really kind of, with multiple rotors in terms of helicopters, there's really 2 configurations which are actually in existence today. So there's the coaxial helicopter, which mostly you'll see Russian helicopters with that design, and some Sikorsky demonstrators, but none that are actually in operation. And then there's the tandem helicopter you saw a picture of initially. So parts of that is if you're basically limited in how much size you have. So if you want to land on a specific let's say a Navy ship or something, and you can go bigger than some diameter, but you want to lift more weight, well, then you basically don't have a choice but to, let's say, stack 2 rotors on top of each other. And it's not going to be as useful as having a bigger rotor, but it's going to be better than just not being able to lift the weight you're trying to. Either that, or for the Chinook, for example, one of the advantages is that you can kind of place the payload you want under it more easily, so you don't have to center it as much with the shaft of the rotor, and you have more kind of margin there. But there's also a reason there's only kind of one tandem helicopter model, except for the one I worked on during a master's, but it's smaller. But it's basically, it works well, but there's no kind of need really to go into that rabbit hole to do a competitor with two rotors.
Pour ça en français, est-ce que tu vois que par rapport aux racers que sont fait une deuxième itération, là, est-ce que tu crois que c'est la limite 400 km/h ou ce design-là peut aller encore plus vite?
Il y a des façons d'aller un peu plus vite, mais ça devient un petit peu plus compliqué au niveau de l'aérodynamique. Puis en fait, un des concepts de Sikorsky, donc coaxial, mais pas exactement juste comme le coaxial qu'on verrait sur un hélicoptère soviétique, va avoir ce qu'on appelle le lift offset blade, mais qui va régler un petit peu le problème de la pale qui revient en arrière puis qui va décrocher. Donc, il y a du potentiel là, mais ça devient vraiment plus compliqué au niveau de la conception en tant que tel, là, où c'est moins un peu rapide, mais il y a du potentiel d'aller plus vite. Mais encore là, en ce moment, la meilleure option pour aller très vite tout en faisant du vol vertical, c'est le tilt rotor. Donc, est-ce que ça vaut la peine de développer une autre configuration qui est peut-être plus complexe, quelque chose qui fonctionne bien en ce moment? Je pense qu'il y a beaucoup des aspects de coût et d'autres considérations là, qui sont moins mon expertise puis moins l'aérodynamique, mettons.
Pour faire suivi avec la question précédente sur le nombre de rotors, pourquoi on voit alors que les VTOL, il y en a plusieurs qui vont vers un nombre plus élevé que 2, puis certains significativement plus même?
Deux, trois aspects. Il y a un aspect que c'est souvent des propulsions électriques. Puis propulsion électrique distribuée, un des points, en fait, c'est que les plus petits moteurs vont permettre globalement, même en somme, à être plus léger globalement qu'un ou deux plus gros moteurs. Donc, si on veut vraiment aller pour un véhicule qui est électrique, pour une raison peu importe laquelle, il y a un gain d'aller chercher ça. Un autre aspect qui n'est pas tout le temps exactement vrai, c'est qu'il y a ce côté-là de penser qu'on a plus de redondance, qui fait que en fait, c'est plus des hélices que des rotors, donc souvent, ils ne peuvent pas changer l'angle des pales, et donc on n'a pas assez d'énergie pour faire l'autorotation comme un hélicoptère. Si tu perds une hélice, tu t'espères avoir plus d'hélices pour pouvoir te permettre de contrôler le véhicule quand même. Certains challenges de plus, donc plus tu as de retard, plus il y a de points qui peut avoir des problèmes. Mais c'est une des raisons là, souvent potentielles.
Donc, merci Mathieu pour la présentation. Pour les étudiants dans la salle, avoir été étudiant moi-même à ce moment-là, si le cours a été disponible et que j'avais été à l'Université de Sherbrooke, pour ça, j'aurais voulu le suivre. C'est le genre de truc que si vous voulez travailler dans le domaine de l'hélicoptère qui va être grandement pertinent. Donc, maintenant, si on passe à la prochaine présentation, je contacte le prochain présentateur à accepter mon invitation, considérant que dans le passé, j'ai dû le larguer comme quelques fois à bord de mon planeur pendant que lui était en avion remorqueur. So our next speaker, Professor David Rancourt, is an associate professor at the University of Sherbrooke since January 2017. He's also a commercial pilot with over 1,500 flight hours. He directs the Sherbrooke Institute of Aerospace Engineering Design and Training, AéroUdeS. He's a co-director of the Createk Innovation Group. He has a doctorate degree from the Georgia Tech Institute. He's involved in more than 40 scientific publications. and he holds 3 patents in the field of aircraft design, air vehicle dynamic, and helicopter aerodynamic.
All right, thanks for the introduction and for the invitation to be here today. I'm going to take different hats during that presentation. One of them is to be an engineer and to lead or co-direct the Createk design group. The other one would be as a pilot and an aircraft owner. It changes quite a bit the way you see alternative propulsion when you see the actual operation of those aircraft. And finally, one of the implications that was not named earlier is I'm also the president of the board of Sherbrooke Airport. So that means I know quite a bit of how regional airports work, funding-wise and investments, and actually this may actually really affect how alternative propulsion will be on the market in the future. Another comment here, I actually put those slides together a couple of days ago, and these were probably the hardest one to put together. I've been working on alternative propulsions for quite a few years now, and first of all, it evolves so fast that any slides created 4 or 5 years ago are not valid anymore. But also, any way that you think about alternative propulsion, especially for vertical flight, the reasoning behind that, simply it cannot be linked to airplanes. Airplanes have different ways to see alternative propulsion than vertical flight, and you cannot really translate the two together. And so hopefully I'll be able to give you that feedback today. So first of all, we're here in the UdeS campus, but we mainly work in the city of Sherbrooke. I always show the slide here showing that Sherbrooke is far from Montreal. It's probably in the middle almost of nowhere, as you see on those pictures. But actually, that's our playground. So we have a lot of open space. We have bunkers to explode pretty big battery packs. We test rocket engines on campus, full-scale propellers, jet engines. And so that allows us to do quite a bit of work related to alternative propulsion. And now, with the link between the Université of Sherbrooke and now the Sherbrooke Airport, we have now about over 700 acres of available field to actually do testing on vehicles. So all that is actually pretty interesting. We actually have some vehicles that were tested on that runway in the last few weeks. Let's look first, before we dive into some more, I'm going to say, editorial thinking of alternative propulsion. Let's look at some of the projects we've done in the past. 2016, we felt that in Canada there was a need to create a demonstrator of an electric airplane. So we launched a senior design project called the Zephyr project, where we converted a glider, a Schweizer from the Schweizer 233 from the Air Cadet program into electric propulsion. And we met with Transport Canada, right? At the time, we were the first one to approach Transport Canada with an electric airplane, and it was interesting. Let's put it that way. And obviously, electric propulsion at the time, that's a 2-seater airplane, and it was converted to electric propulsion with its static test. And at the end, it was just a single-seater airplane because we converted one seat just to battery packs. Not very good for flight training applications. A couple of years later, we launched an all-electric airplane program called the AERA project. About 30 students over 2 years designed and built this electric airplane. So it's a retrofit aircraft. They designed the battery pack from scratch, all the avionics, and did some ground testing, again, just to shake a little bit the industry and the regulatory groups in Canada. Again, Transport Canada was involved in this. But finally, we actually published all the numbers. We just went out there and said, these are the weight breakdowns. This is the efficiency. And so that kind of put a lot of information out there. Obviously, there were some lacks in terms of capabilities of that aircraft. So we developed a hybrid electric program called the HARP project. A group of students designed and built the first hybrid electric powertrain. It was a Rotax 912 IS combined with an electric motor, and it was able to charge and essentially charge the batteries, discharge the batteries, combine the internal combustion engine with the motor, and so that led to a very interesting actually result. Right at the start, when I still recall when Marc Saint-Hilaire from CE gave me a call around 2019, he said, we're looking to build an electric airplane, please jump in. And so we've been working with them on multiple parts of that program since 2019. With Pratt & Whitney Canada, we launched the HEPOS Hybrid Electric program. So it was essentially a conceptual study of putting a parallel hybrid powertrain on the Dash 8, which led to very interesting results regarding the emergency cases of hybrid electric powertrains. The follow-up of that, we're still working now on the AP project with Bombardier and Pratt & Whitney on what are the alternative propulsion systems that can work on business jets. Just to give you an idea, if you take a global or let's say a Challenger business jet and you want to put hydrogen in it, if you put liquid hydrogen, you have to put 100% of the fuselage filled with liquid hydrogen to be able to meet the needs. So there will be no passengers. So that becomes, well, not a very interesting aircraft. So these are the real challenge of those applications. And in parallel, we worked for the last 20 years on developing ultra-high efficiency gas turbines that are really well, that could really well work on vertical flights. And so I'll give you more details. And obviously, probably 20 confidential projects that I won't be able to talk about today. But before we go further, it would be easy to start by just talking about different architectures. But we always forget the why. So let's start the opposite way around. Why are we talking about alternative propulsion for VTOLs or vertical flight? The first one, which is really obvious, is an environmental footprint. We want to minimize the impact, right? We want to minimize the emissions. But what emissions? Could be CO2, could be unburned hydrocarbons, could be just lead, right? Avgas today contains 0.5 gram per liter of lead. It's the largest emitter of atmospheric lead in the world. Could be we want to reduce some of the soot from gas turbines combustion. But in-flight emission is not all. If you produce your fuel with not so clean sources, and so you consider from the well, so essentially when you create the fuel up to the wake, essentially the emissions of the aircraft, that might not be positive, right? So we have to consider, do you want to consider the whole emission just in flight, the well to wake, or the whole aircraft life cycle emissions? And that's the point I want to talk later today. Well, if you have an aircraft that is 3 or 4 times bigger than the conventional aircraft, you might have less emissions in flight, but at the end, are you really greener? So that's the first one. Well, noise. Maybe you're not allowed today to fly in some specific parts in the city because of noise. If you have let's say you reduce noise, maybe you'll be able to do so. Cost, and that's a hot topic. Do you want to reduce the operating costs? Do you want to reduce the ownership costs, the energy costs? Well, it's a mix of all that. And maybe some concepts will meet some of that, and some of them maybe not. And maybe you'll have some numbers that are essentially hidden. If you just consider energy costs for an electric aircraft, you'll realize that you might be missing a major part of the cost, essentially. So these are, I guess, the most obvious ones. But there are some non-obvious ones that, if you read in details and use, you might have some insights about it. IR signature. Alternative propulsion is a way to reduce the infrared signatures for military applications. Right. Military is all about performance. Why will the military invest in electric aircraft in the US? Certainly not because they're supersonic or they can carry tons and tanks. It's because there are very specific missions that you might not want to be seen at all on radars. Maybe you want to develop alternative propulsion to enable new capabilities, right? So that might not be to really reduce environmental footprint. It might just be because you want to have an aircraft that goes faster. Maybe you want to have an airship that you want to go backward, up, and down, and I'll give you some examples of that later. Maybe you want to improve customer experience. An example, you know how much it costs to have, let's say, air conditioning systems on a Cessna 172? If you buy that today, it will be about $50,000. Oh, and by the way, you can't really start that AC system until the engine runs. So how about if you have alternative propulsion, you have just a slightly larger battery that allows you to start the engine, that allows you to program all your avionics, but also pre-cool your cabin. People will be able probably pay $100,000 for that options in the US. Right? So these are alternative cases where alternative propulsion might actually enable that. Electric taxi. I've flown helicopters where you have to start a turbine, take off, and land 50 feet, let's say 100 feet further. to finally put some fuel in the helicopter because you can't taxi because there's no taxi closure. Well, if you can just use the electric powertrain to taxi and not have the rotor spinning, now you're adding some more elements. Maybe that you can maybe sell more helicopters in that case, or make your product more interesting. Increase safety, right? So alternative propulsion systems sometimes are combined with, let's say, electric emergency systems for rotors. I'll give an example of that later. Or it could just be a tech hype, right? There are cases where we want to showcase new technology, and we just have to realize that this might be the case. So let's look now at the different architectures and who's worked on each of them around here. So alternative propulsion, there are multiple definitions, but let's say we have all-electric concepts. We have hydrogen-powered concepts. We have hybrid electric, basically using fuel. Internal combustion engines that might be used for vertical takeoff and landing aircraft, or basically brand new engine concepts. So hydrogen, you can have multiple approaches. You can burn it, or you can put it in a fuel cell. Hybrid electric, you have series, parallel, and a mix of all that. Internal combustion engines, you have brand new technologies for ICEs, but you can also have turbo diesel applications, and I'll give an example of that later. So you see there's so many concepts, and the thing is, each of those propulsion architectures may or may not be compatible with physical aircraft architectures. So that becomes a really complex problem. You have on one side the propulsion architecture, and the other side you have the actual aircraft concept. And this is where it gets really complicated. So let's look first at all-electric VTOL propulsion. First of all, the first flight of a manned aircraft with electric propulsion on the Robinson R-44 was done in 2016. First cross-country flight between two airports, and believe me, these are pretty close airports, in 2022 with Martin Roblat, the CEO of the company that funded the project, as the pilot herself. You have the Robinson R-66 that was just announced a few weeks ago, where they plan to take the bigger version of the Robinson aircraft and convert it to electric propulsion. And you have all the other concepts, and we're not going to go through that today, but there you can have, the Lilium with over 30 propulsors here. You have the all-electric Whisk aircraft, Beta, Archer Vertical, and Joby, sponsored here. So why would you want to go with, let's say, the less efficient concept that Mathieu presented earlier? Well, it's easier, not easy. It's easier to certify, most likely. And that's the approach that Robinson has been taking, because you essentially do an STC. So you modify it. It's like changing the brand of an engine. You can do that on a vehicle pretty easily. So that might be a way to get in the air faster. You have a reduced power requirement in hover because of the low disk loading. However, cruise efficiency is low, and I'll give you a couple numbers later. If you look at on the right, all those novel concepts, they have a really higher cruise efficiency. They can have a reduced noise. For example, a Joby aircraft, they take off with 1,000 RPM on the props, but they cruise at 250 RPM with less than Mach 0.35 at cruise. So that's how they get really low noise, and that would not be possible with gas turbines. However, complex certification, really high empty weight ratio, and essentially it simply uses the electric propulsion as an enabler of those architectures. None of them could work if they were not using electric motors. Let's do an example. So I have here just a very simple lithium-ion battery, like the ones you'll see on Teslas, but also on electric airplanes. We're going to do a very simple sizing case. So let's assume the following characteristics. Let's say we have a relatively low efficiency rotorcraft with an equivalent lift to drag ratio in cruise of 3. We have 50% of the mass, that is the airframe, the motor, the seats. And we put 25% of the weight of the vehicle to be the batteries. Essentially 25% left will be the payload. We assume about 200 watt-hour per kilogram that is usable. You can only do 55 kilometers with that rotorcraft. That's a theoretical maximum distance you can do if 25% of your rotorcraft was filled with batteries. So we're not like the Tesla case where you say, we're just going to put more batteries, it's going to work. If you put more batteries, you're reducing your payload. If you put 50% of the vehicle to be batteries, you have a remote control helicopter with no payload, right? So that's the harsh reality. So if you want to have 500 kilometers like the original aircraft had, it's a 10-fold increase in battery energy we need. If we don't do that, let's say we just have half of that increase, and you say, well, you know what, let's make the helicopter bigger. Let's just make bigger, let's put more batteries in it. You get into the weight growth approach, meaning you'll get a helicopter that 10% of the helicopter will be payload, 40% will be battery. But if you wanted to carry a ton, now 10% of a ton, right? Well, it becomes a 10-ton helicopter. So you get into that increase of size. So it's not about increasing by 10 or 20% or just pushing engineering to say it's going to solve the problem. It's not, right? We need new chemistry in the long run. Or essentially focus on very specific applications that 55 kilometer is sufficient for, let's say, 99% of the company's operation. So in this case, 55 kilometers of distance at, let's say, 80 knots, which is a pretty efficient cruise speed, that gives you 23 minutes of flight time. Well, today, you need 20 minutes of reserve to fly a helicopter. So that leaves with 3 minutes. So that's the reality, unless we change the reserves also at Transport Canada or the FAA, right? So at the end, we're not close. We're not even close for electric concepts to meet how essentially the original helicopters or aircraft are in terms of performance. And be careful, most of them are much heavier, and there will be consequences to that. Give you just an example of an airplane. So that's the one I used to fly. I sold it last week. The Cessna 210. Just to give you an idea, that aircraft was built and was flying. That unit was flying before we walked on the moon. Okay, so that gives you, the time from the Cessna 210 Bravo version. 63 gallons of fuel. So let's say you top it off. You replace that 170 kilograms of fuel by batteries. You assume 250 watt-hour per kilogram. Then you assume 85% efficiency on the motor and drive. And it needs about 165 horsepower at high speed in cruise, so 140 knots in cruise. Let's neglect the takeoff. Gives you 20 minutes of flight time. You fly 90 kilometers. This is a flight I did last year. I flew from Bromont with my family on board, landed at Prince Edward Island. That's a 3-hour and 15-minute flight, 780 kilometers, and I used 60% of the fuel tank. So that is, again, the harsh reality of electric airplanes, right? Electric propulsion. It's not about, we're almost there, we have to double the battery capacity. No, it's a 10-fold difference to actually meet an aircraft that was designed back in '62. And nowadays, two-seaters with the recent engines can actually cross the ocean on 120 liters of fuel. That happened last year, right? So again, let me just take away here. So for now, all electric aircraft are very far from getting the range of conventional aircraft. So it's not the current customers that are actually going to buy those aircraft. It has to be a new customers that are pretty much satisfied with very short range. So it could be trainings, it could be local flights, urban air mobility on very short distances. And again, the clean energy must be available. If you charge that using a generator, well, you're just better off burning the diesel directly in the aircraft. So we did a conceptual study, Mathieu, back in the days, and I, in 2022, where we tried to assess the environmental impact of electrifying a light aircraft. And in that paper, what's really interesting is we also did resizing. And one of the conclusions was the following. So if a propulsion technology is heavier and thus reducing the actual aircraft payload, if you take a 4-seater and becomes a 2-seater, it should be compared not with a 4-seater aircraft, it should be compared with a much smaller 2-seater aircraft with reduced capabilities. And that is a major flaw that we see at least on 75% of the conceptual studies. And again, clean energy must be available. Give you an example. So that's an aircraft a couple of years ago. It was announced with the Magnet, so a Cessna Caravan, electric propulsion. They expect 100 nautical miles of range with 4 or 5 passengers with batteries, about 1 ton of batteries on board. And it with very slow flight speed, best L over D. Well, should you compare it with the original turbine-powered Cessna Caravan? Well, hopefully not, because you're comparing essentially a scooter with a Harley-Davidson, right? So you have to compare it with an aircraft with the same capability. Now, which one has a less environmental impact? The one that the takeoff gross weight is 1 ton, or the one that has a ton of batteries on board? So we always have to go back to compare with the right matrix, and that is, I think, one of the key takeaway here. Just make sure that, and I'm positive and really for those new alternative propulsion technologies, but just make sure we do fair comparison and use the right matrix when compare them. One example is the electric DA40 that we studied in the paper. If you take a 4-seater aircraft like the DA40 and then you remove 2 seats, well, it's not a DA40 anymore. It's a DA20. That's a 2-seater version, right? So we just have to, again, do the right comparison. One way to mitigate the very low efficiency, energy efficiency of batteries is to go with hydrogen. And really interestingly, the first helicopter in the world to fly with a fuel cell was done in Bromont this summer. And it's Unitors H2 powered, the R44, with the picture that you see here with the steam coming at the back of the fuel cells. Joby has done a similar approach with their aircraft without anyone on board, using liquid hydrogen. Essentially, I'm expecting, and Unitor is also doing this modification, it will all be liquid hydrogen for those vehicles, just because of the efficiency and the size of the system. However, the fuel cells are still heavy, right? They are still they're really, really heavy. So you're reducing capability of the aircraft. The hydrogen-powered R46 is not going to have the same range and payload as the one with alternative propulsion. But it's still a pretty good step forward, and I'm pretty sure hydrogen for a vertical flight is one way to go. Again, if you know where you're going to essentially fly, and not have, if you accept that you're not going to have the flexibility to go anywhere, you're just going to want to go from point to point, I think it's a good option. But you still need clean H2 to start with. If you produce that H2 from let's say any source that is essentially isn't clear, and you have a heavier aircraft, so your fuel must be pretty much clean. Otherwise, you will have a higher environmental impact. And one approach with fuel cells to improve the efficiency, not in terms of efficiency like we define it, but in terms of weight, is to go with high-temp fuel cells. It was announced a prototype should fly pretty soon with those high-temperature fuel cells that are much more power dense. There's no liquid to deal with because it comes out as steam. Some preconditioning is required. High potential, but yet we haven't heard back in the last few months where that project is. So expecting that there might be some hurdles, technical problem there. One approach that I think has been understudied is hydrogen combustion. Why? Because we say hydrogen means fuel cells, it's electric. But at the end, if you take hydrogen and you burn it carefully, why would that not be a good option, right? It's still, hydrogen can be produced using hydroelectricity, clean energy, and so the hydrogen is essentially an electricity carrier. If you burn it, then you have less of the problems of electric propulsion today in terms of having to deal with the fuel cell and water and the density and what you do in the winter. So hydrogen combustion has this higher power density availability. It could be a turbine, it could be an internal combustion engine compared to fuel cells, and no need for batteries. Challenges, there would be NOx production, materials, embrittlement, and there were multiple challenges. But yeah, there's still a pretty high interest. So RTX just announced that there will be a test with hydrogen combustion, and the company has done some hydrogen combustion back in the days, if you look at the literature, because it is a pretty interesting approach. Recently, the Rotax engine was converted to burn hydrogen. So look at those options. Now we can burn hydrogen in a certified engine. Well, the engine is not certified anymore because it's modified, but yet it has been done and it works. So it is an alternative system that should be considered. And combustion allows for one important thing: dual fuel concepts. And dual fuel concepts is the enabler for the transition between two technologies. If you can put jet fuel or hydrogen in your engine, well, that's a way that you can fly to any airports today. we did a demonstrator with a 3-fuel internal combustion engine, hydrogen, methanol, and conventional fuels, and we were able to switch as the engine was operating the power source. And we believe that might be a future, interesting future. Hybrid propulsion, well, vertical flight, I wasn't sure to put an airship here, but it is part of the vertical flight, approach. They announced that it will be also creating the manufacturing facility for North America in Sherbrooke. So Flying Whales is a series hybrid airship, although I think it hasn't been announced that very publicly, but recently, yes. But they have a 4 megawatt powertrain. So gas turbines are going to produce electricity, and that electricity will be shared on the whole airship. Batteries are used to dampen all the peak powers in the system, and then you have 32 propulsors with 4-meter diameter props. So it's a pretty massive system. But at the end, why are they doing it? Well, because the airship, they want to be able to move up, down, backwards, sideways. So you're not going to put 32 internal combustion engines. You're not going to put 32 gas turbines. But you're going to have 4 gas turbines with 32 electric motors. Right, so alternative propulsion here is a mean, essentially, to enable the new capabilities on the airship. Pretty nice example here is the Horizon aircraft. Same approach here, except it's a parallel hybrid systems. So a turboprop is used to push the aircraft. Electric propulsion is only used for takeoff and landing with the ducted fans within the wings. Pretty interesting concept when you have the leading edge and trailing edge moving out to open, the space and put the ducted fan in. But the reality is, they're not going to need any ground support. They're not going to need chargers. Their vision is to use a gas turbine to charge the batteries. So it's only a system designed to improve the capability of the aircraft. No alternative propulsion here. No way to have this 250 knot aircraft flying. It's not about efficiency in terms of environmental impact. It's about performance and capabilities and customers to be happy to fly 250 knots at low altitude. Right. And by the way, they use the heat generated from the batteries to de-ice the leading edge. So that's it's a very synergetic system that is quite interesting, and they have a half scale system already flying. And it's a Canadian company. Hybrid propulsion, you can look at different concepts. Jaunt now is officially announced that they will be making this aircraft, designing and making that aircraft in Mirabel, series hybrid powertrain. And again, it's the alternative propulsion architecture that allows that aircraft to actually fly. Hybrid propulsion in general, we should not refer to hybrid propulsion as range extenders. All the concepts that we studied that's saying, we're going to use electric power, and then if you want to go further, let's turn on the turbines or whatever, at the end turned out to be essentially not a positive in terms of efficiency at the aircraft level. There's a hybrid propulsion system. Either they have to allow for an increased efficiency in the gas turbine or the engine itself, so there has to be parallel hybrid and mild hybrid system to improve the gas turbine efficiency, or increase the aircraft capabilities. Let's look at that tail rotor, right? It's electric power tail rotor. That falls under the alternative propulsion systems because you're taking energy for the main engine, convert that to electricity, and then using that to power another systems on the aircraft. Rotorcraft can gain in safety by adding a very high power system directly on the main rotor. A 100 kilowatt system that can work for 30 seconds with very high C-rate batteries. That allows single engine to essentially better auto-rotate and reduce the mass in the main rotor because there's a mass added on single engine helicopters for auto-rotative capabilities. And that has a pretty small limited gain in weight. Alternative engines. Turbo diesel now is something so that at the lower left it's actually a drone, but it's a 1,000-pound drone working with a turbo diesel engine. Flight capability, 10 hours flight time. For Rotorcraft, that's a pretty amazing with a 40% efficiency engine. Turbines with new thermodynamic cycles, over 35% efficiency with sub 200 kilowatt systems. Again, very novel architectures. Or internal combustion engines, right? We can bring those back into a twin engine approach where we don't like the reliability of internal combustion engines, but if you have two, that might be better, and that allows to burn hydrogen pretty nicely. I'm going to skip this one just for time. So what are the main challenges, right? So I presented a couple of challenges here and there, but I want to present one that is really critical, and I'm going to put the hat of an engineer here, but also the president of the airport. It's called infrastructures. So here's an example. Well, batteries should be kept at near room temperature for optimal performance. That's interesting. But hangar space, cost, and landing fees depend on the aircraft size and weight. Currently, it costs quite a bit if you land a twin engine, 6,000-7,000 pound at an airport. You're going to easily have $100 to $200 of fees to land. Alternative propulsion aircraft are generally much larger and heavier. Suddenly maybe the cost would be higher to land at different airports. A hangar for the Betas Alia 250 aircraft on the lower right part will easily cost $1 to $2 million at the regional airport to put that aircraft in a hangar. While if you look at the King Air on the left side, that's a 10-seater aircraft, will stay outside at minus 40, turn the engine on, and you'll still take off. So again, that's a cost that should not be underestimated. That's a picture I took when I flew to Savannah International. That's an FBO. Well, FBOs usually work. You ask for fuel, they take a truck, and they top you off at the parking spot. You're not allowed to take your aircraft and go to the pumps. If you have a 20 electric-powered aircraft, you're going to have like high-power conductors under the pavement and new facilities. It's not possible to take an aircraft and book a full spot at the fuel tanks for an hour. So how would that work for a large fleet of aircraft? An FBO price depends on the aircraft size and required services. So you see the jets in front at the right part of that figure. Well, it was probably about $1,500 to $2,000 a day to be there, while my Cessna 210 was $30. So the reality is, if you take the space of a King Air, while you have the performance of a Cessna 210, you might be surprised by the bill you'd get at the end. Electric chargers, they require a significant investment, both from the charger itself, but also the power line. So Sherbrooke just added a new power line to be able to handle the increase in power requirement of the airport. And we're probably close to $500,000 investment just for that power line. And we cannot charge 5 aircraft at the same time using that line. Similar challenges will exist with hydrogen, and today's budget from the government level to fund regional airports to put those chargers in place is none. Right now, there's no way to fund that using government funding. So the true first customers, I believe, for those technologies will be operators that will do point-to-point operation over very short distances, and the operators will actually cover all the costs associated with those infrastructures. And flight training operation, that's interesting. You always land and take off at the same location. Conclusion, just for food for thought to think about that as we take a last drink later today. Here's a flight I did with one of the aircraft, the Midget Mustang on the lower right. That's a 1950 design. I flew from Sherbrooke to Ottawa for a meeting. An hour and a half flight, 27 liters of fuel for the total flight. That flight using electric aircraft will take 2 days because I will have to stop 6 or 7 times to be able to do that distance. And it was, that aircraft is powered by a 1950 Lycoming engine. So that is the true reality of electric aircraft, both for the VTOL application and conventional. Well, we say electric makes aircraft quieter. Here's an example. The world record of the quietest aircraft was done in 1969. It was an internal combustion engine with a good gearbox and exhaust system. Again, electric propulsion is an option, is a solution, is a technology, but it's not the only one to consider. Last slide. The alternative propulsion here is I think, there's numerous reasons why you want to go there. It could be for reducing environmental footprint on very specific short distance concept. You might want to use hydrogen for longer distances, but you're not going to be able to replace conventional rotorcraft or conventional aircraft with a purely electric or hybrid electric system. It can be an enabler for advanced concepts. and like flying whales airship, or multi-rotor systems, or Horizon's 250 knot helicopter. And that enables new capabilities, right? So it's not all about environment. Sometimes it's about performance and meeting the customer needs. Always use the right metrics. Big aircraft carrying a very small payload is not a big aircraft. It actually should be compared with a small aircraft. And electric propulsion is not the only option. There are multiple others, and I feel that in the last 7 years in Quebec, we pushed on electric. We pushed on hybrid. But it was more technology push than a technology pull. At the end, we forgot, or I've seen companies, partners that said, I cannot fund that project because there's not the word electric in it, right? So just be careful of that. We have to listen, to the reality of the market, and essentially listen to customer needs, because at the end, we need to have those aircraft flying for all those initiatives and companies to go forward. Thank you.
So first of all, thank you for the presentation. Just wondering, why do you think a lot of the eVTOL companies will market a hybrid concept for military use and then an all-electric for the commercial side?
Good question. So, well, hybrid electric is the only way for those concepts to actually do a real mission, right? Outside remaining in the city and doing just short hops. So for the military, hybrid electric is, for example, the way to go to a destination, stop your internal combustion engine, kill the IR signature, do your mission, relight, and leave, right? So that is one reason. The military also is in the US is a pretty major source. So I did my PhD there, and you'll see the military will give funding, sometimes even at some cases where I technically may not make sense, but they know it's going to help the company to grow. Right, so that is definitely a reason. And on the civilian side, there has been this vision by multiple companies, and that it has to be all electric. If you put something hybrid, you're not clean enough now. And so I think there's still this vision of you need to be all 100% electric, and the last resort is hybrid, and that's why I think the military is going that way.
So I'm not that familiar with hydrogen combustion, but my kind of limited understanding of it is that it's still somewhat volatile and it's hard to control. So how would you mitigate those risks and also convince the general public that these technologies are safe for them to fly on in the air?
So hydrogen, one of the risks is first it leaks, right? You think about the leak, it's leaking, right? And whatever ratio of hydrogen to air, if there is hydrogen, it will burn. Okay, so that's the real risk. Now, hydrogen combustion has been used for years already. So cars burning hydrogen have been tested, and at some point we think if we think that hydrogen is dangerous, well, batteries are also dangerous, and so convincing people to fly in a hydrogen-powered aircraft, I don't think it would be that complex. But of course, there are risks to consider.
To carry on his question, isn't hydrogen also a lot less energy dense than other types of liquid fuels?
Good point. So yes, liquid hydrogen is less dense. For vertical flight, it's not that a problem because you don't go fast in the aerodynamics. You can put a tank, and that is still viable. For business jets, for example, it's pretty hard because you need a pretty major tank. But at the end, it's still better than batteries. So and again, I like batteries, electric aircraft. I flew electric aircraft before, but in terms of volume, there is a way in a helicopter to put a liquid hydrogen tank that is big enough to do a meaningful flight. Okay.
Hi. So in terms of the certification aspects, I find there's a lot of push from the industry saying that the certification is really slowing us down a lot. How much would you say that's really true as opposed to, as you point, the immaturity of the technology itself?
That's a good question. I guess it's probably both. On one side, on one side you had Joby and Beta having very complex flight control systems. On the other hand, Boeing killed 500 people by crashing an aircraft because of a stall limit. So the reality is we cannot use those. You have to be sure that the aircraft will react properly. And when you combine new propulsion system, batteries, new flight controls, new aerodynamics, vortex ring states, and no auto-rotation capability, no parachute because you can't afford to have a parachute because of weight. When you sum that up, in some cases you don't even have a pilot on board. I think there is definitely a role by the certification authorities to break a bit and make sure that it works. Now, do they break too much? As long as they're allowed to do flight testing and actually get flight time. Hopefully one of them will be certified soon, but soon will be a couple years down the road.
You mentioned dual fuel concepts being interesting for hydrogen. For those who attend a lot of VFS events, about 2 years ago, we had someone come in and talk about the differences to a jet engine if it's going to burn hydrogen because the molecule is so much smaller, you need more holes. Like you said, it leaks. How practical do you think it really is to have just a junction in the fuel system where you turn it to hydrogen or you turn it to Jet A1?
On conventional gas turbine, I think it's pretty hard. And I'm not an expert. I think there's quite a few people in gas turbines in the room that may talk a lot more than me on that. However, that's where I think rethinking gas turbines, so there's a company in Sherbrooke that's a spin-off of one of the research, where actually we have dual fuel injectors. So the engine is designed with the ability to flip the switch. But you have to think about the combustion chamber to be designed appropriately right at the start. Now, is that an easy fix? Probably not. But I think some of those options, for example, dual fuel combustion, especially for vertical flight applications, have just been pushed aside. And I think they might be realistic at some point.
Merci à tous. Avez-vous d'autres questions?
So a lot of this is, my understanding, driven by an environmental push. How risky is it to have a technology that is not within aerospace that helps decarbonize everything and then all those projects vanish?
You have an example?
Well, I mean, giant fans that suck carbon out of the air, but that's not scalable today, to my understanding. But anything else. So essentially something that will, outside aero, decarbonize, the air, something maybe outside of the box, and then you won't need those technologies.
Not sure that's quite realistic, but definitely one thing that we should consider is, e-fuel or SAF. Obviously, it's not going to solve all that, but if we had clean fuel, and I'll give you an example, you can buy in Germany today clean fuel, e-fuel for internal combustion engines. You'll pay about $4 per liter instead of $2 for airplanes. That's a lot, right? $4 per liter. But if you cross the ocean with 120, don't really care about the $2 difference. Right. So the reality is there are alternatives, and I think if we get clean fuel at the source, I think we could get some pretty clean VTOL concept, which might be just a pure Robinson R44. I mean, it could be relatively clean. It doesn't going to solve some of the noise, doesn't going to solve in-flight emissions, but on the life cycle aspect, it might actually be better than flying, a 5-ton aircraft.
So you think that the development on those alternative technologies is going to continue regardless of what is developed in other fields, SAF, for instance, or other things we don't think about today?
Yeah, I think there will be work in parallel, and it has to be because commercial. So we just focus today on vertical flight, but when you look at commercial transport, there is no other solution. There's just no other solution. Hydrogen for most of them is not even a solution. It has to be SAF. You take, like I said, a business jet, you put it in hydrogen, you have no fuselage anymore. You need a twice as big aircraft. But at the end, it's going to cost you so much, it makes absolutely no sense. And that's for a Challenger-sized aircraft. I'm not talking about the Global, right, which will be even bigger. And business jets, for example, they tend to go to regional airports. Like we get at least two or three a week in Sherbrooke. Well, the reality is, if I don't have liquid hydrogen, they will be stuck there. And so most of those, I guess, companies and concept, and essentially the ones that are burning 90% of the jet fuel today, they are focusing on SAF to be the main solution.
Thank you.
So I was wondering if you had an opinion about something like solar-powered airplanes.
I'll give you an example. Solar-powered airplanes. Except some very specific demonstration 10 years ago that they flew around the globe with a solar aircraft. Just give you an order of magnitude for an airplane. A Boeing 787 on takeoff will need the power of all Sherbrooke City electricity supply. That's the power of the fans on takeoff. If you cover the wings with solar panels, you'll be able to probably power the air conditioning system on the aircraft. Now, so it's not even close by orders of magnitude that we can get solar aircraft really flying today. And that's the sad reality. And when you go to the system level, where aircraft must be able to be, de-ice, you're going to put fluid on them. It's going to ice, and then you have those eating elements on the leading edge. And you get to a point where, and the additional weight, is going to essentially add more fuel consumption on the aircraft than its gain. So, give you an example. If you take that battery and you say, I'm going to power a commercial transport aircraft with that battery. If you put it on the aircraft and you say, I'm going to use all the energy in that battery to power a system, at the end, that battery will cost you more fuel to have it on board than all its energy content. So that's the difficulty with aircraft. We have no margins. And so adding solar panels is a great way, I guess, to showcase technology. But on the realistic side of things, sadly, it's not going to make the cut.
Thanks.
Sorry, so you said that you've flown a electric aircraft before?
Yep.
Like fully electric?
Yes.
Can you talk a little bit about like the difference between flying a normal aircraft versus the electric?
First of all, it's pretty amazing, right? No, I really liked it. It was a couple of weeks ago, and there are a couple of differences, and I'm going to maybe translate a little bit from maybe non-pilot. If you take an airplane and you put to idle, because if you want to taxi, you want to circulate with an aircraft on ground, you put power, you accelerate, you put to idle, and you're just going to keep going because of the prop is spinning. On electric aircraft, the prop is spinning all the time. You're not going to stop the prop from spinning, but the idle is actually no power or near no power. So first thing I started taxiing, put the power, accelerate, put to idle, the aircraft stopped. I'm like, shit, I forgot to keep the power on. And then in the air, it's pretty amazing because you fly. It's a little more quiet. It's not as quiet as you think because wind is going to hit the canopy and the prop is still making that pretty big noise. Maneuverability, well, it depends on the aircraft, but the one I flew with the Bristol B-23 was a pretty nice aircraft, pretty maneuverable. I really enjoyed the flight. Flying and landing is good. I mean, I really liked it. Would I fly that aircraft again? Anytime. Will I bring people on board to look at the technology? Hopefully, I'll be able to do that later. Would that be my personal aircraft? No. The reason is, if I want to fly from Sherbrooke to Saint-Hubert, I have to do 2 stops. All right, and it will, and I need so from a with today's technology, and even in a few years from now, I may be able to hit in one flight, but I'll use 80% of the batteries, and I'll be maximum. But then at the end, it won't fit my needs of flying to Prince Edward Island with the wife and kids. So really nice experience, really interesting. I think really the dashboard and the handling, and it's a really nice experience, and I hope you have the chance to try that one day. But it has, the real benefit is for very specific applications where range is not critical.
So like in terms of drivability, no, just the range.
It's only the range, because let's say you take that aircraft and you take a Cessna 172 beside it, and you were to take off and climb. The B-23 was winning over the 172, and it was extremely gusty that day. Cessnas were just flying around, and it wasn't that great. And I landed the aircraft like there was no wind, right? It's a pretty nice aircraft to fly. We used I have to check the numbers exactly, but I think it's 18% of the batteries within 9 or 10 minutes of flight time. So we took off from Saint-Hubert, did a couple of turns, and landed, and we used about 18% of the batteries. It's okay when you want to do flights like the Air Cadet program, when you want to test a couple of stalls, you come back. But for let's say I'm going to fly, like I said, wife and kids across the country, it's probably not realistic today.
Thank you.
Merci à tous. Thanks. Yes, so just before completing our event for tonight, we'd like to talk a bit about the upcoming event for the VFS. I know it's not maybe very in the near future, it's next year, but we have the Forum 82 that will be at West Palm Beach, but one in May 5 to 7. If you, for the student, or if you would like to publish a paper for this conference, just remember that the due date for the abstract is at October 6th, so in a few weeks from now. Other thing also, this is mainly for the students again, but at the local chapter here for the VFS, we have the Litchen Award, which is an incentive to present to the forum for the first time. What we will do is that just reach out to us, and if we organize a local competition of our presentation, and the winner will win a free pass to have an access to the Forum 82. And what we do is that we collect the winner for each local chapter, and the winner from all the North America will receive a $500 award and all the travel fees paid by the VFS. So we'll give you more information regarding that in the following month, but usually the competition is in January. In January. If you would like to join the VFS chapter, we have still some place available in our chapter for officer. Or also, if you have an idea or a person of contact who you think will make a good event, you can reach out to us, and maybe like the VFS can be the bridge between your idea and event like the one we are doing tonight. Before ending this presentation, I would like to give a special thanks to the two presenters that presented tonight, David and Mathieu. We also have a gift for each of you. Thank you, everybody. If you want to stay and continue the networking session, we still have a bit of food available in the table in the back, and enjoy the rest of the networking session. Thank you.